Good morning, everyone. This is Shauna, and I'm here in this video to show you a little bit about a technique called approximate integration. We're going to be approximating the value of an integral rather than using a specific technique to evaluate it directly. So this comes from section 7.7 for those of you who are doing the Stewart book. And this is problem 7 from that section. It reads the integral from 0 to 1 of the square root of 1 plus x cubed dx. And we want to use 4 subdivisions. So what I've done here is I've given you a little checklist over here because this section asks you to approximate using 3 different rules: the midpoint rule, the trapezoidal rule, and Simpson's rule, or the rule of 3. So here, I'm going to show you all of 3 of those methods, but I'm going to remind you that you did do some of this back in Calc 1 when we did the left endpoint approximation and the right endpoint approximation for the rectangles. This is a step up from that. You probably did the midpoint and the trapezoidal approximation as well. Maybe you don't remember the trapezoidal, but the midpoint you definitely did. So the way this works is we take this function, and if you graph it, we divide it into however many subdivisions we want. In this case, they gave us 4 subdivisions. And you have an interval, a finite interval. In this case, we're going from 0 to 1, and we're dividing that interval into 4 parts. So we have what we call the delta x, which traditionally we think of that as the height. So delta x is always b minus a over n, okay? And this formula changes slightly for the trapezoidal rule and for the Simpson's rule that we'll see later. But this delta x is pretty standard. So we have 1, where's it coming from? B is the upper limit of integration. So b minus a is the lower limit, over n, which is however many subdivisions you're making. So that means that my delta x is 0.25 or 1/4. Now, for the sake of putting it in the calculator, I made these decimals. This wasn't too bad. So this is 0.25. So my interval starts at 0 and it's 0.25 units wide. So 0 to 0.25, 0.25 to 0.5, 0.5 to 0.75, and 0.75 to 1. Okay. Now, my heights, if you look at this little kind of checklist I have for you to follow, which rule are we using? We're using the midpoint rule. We found our delta x, which means we had to identify a, b, and n. We defined our interval, which is what I did right here for you. We then find the heights. The heights are f of, now, notice here, where did I get this f of 0.125 from? Well, the middle of 0 and 0.25, this is the middle of 0 and 1/4. The middle of that is 1/8. And so 1/8 as a decimal is 0.125. If you want to find the midpoint, add up the ends of the interval, so 0.25, and divide it by 2. Here, add up 0.25 and 0.5, that's 0.75. Divided by 2, 0.75 divided by 2 is 0.375. 0.50 plus 0.75, this is 1/2 and 3/4. this is 5/8. So 0.625 and so forth. Here, this is 7/8 is the middle of this interval, f of these numbers here. So the midpoint with 4 subdivisions for this is going to be delta x, which is 0.25, times f of 0.25, sorry, 0.125, f of 0.375, plus f of 0.625, plus f of 0.875. Okay. And all I did was plug those numbers in. Now, when you plug this into the calculator, there's a lot of decimal numbers that you're going to get. There's a couple of ways to do this. So I'm going to show you on the calculator what I did. And in general, the book rounds to 6 decimal places, which is why you see my 7 underlined. I did get the same answer as your textbook, but the textbook stopped here. So let me show you that 0.125, 0.375. So we're going to, there's a couple of things you can do. One is you should start by putting in the function into your y1. Okay. Now there's a couple of things you can do from there. You can set your from here, you can set your table, second table. And that's exactly what you see me do here. This is 0.125. And notice, I'm going to show you something here. Second table set. I go to table set above window. Notice that I have my independent variable, that's my x, on ask, and my dependent on auto. Okay. So one of the things you can do is go and say, okay, I'm going to go back here, go to my table again, second table. And if you put in, let me show you. So if you put in, if I put in 0.125, I'm going to get this number out. It'll just spit out numbers. Now be aware that for screen display purposes, you'll only see 4 or 5 decimal places. Usually 4, but sometimes 5. But your calculator stores more than that. So go ahead and feel free to take 6 places, 1.000976, and write that. What you're basically doing is adding up all of these and then multiplying by your delta x. So here, you can either do that individually, or the other way you can do it is to do this. The other way you can do this is to say, what I'm going to do is I'm going to use, I have my function in y1. So what I do is I go to my delta x, which remember was 0.25. So I take my delta x and I multiply it. Now watch what I'm going to do. I'm going to take 0.25 and I'm going to say, okay, I'm going to go to vars, y vars, my y variables, my function, which function? Wherever you have your function stored, which for me is y1. And I'm going to tell it that I want it to find my numbers, 1, 2, 5, plus, then I'm going to go vars, y vars, function, y1, and I need, the next thing I need is 3/8. So that's my parenthesis, okay, 0.375. Then I have my vars. So plus vars y vars function. Oops. Sorry about that. Y vars function y1. This is going to be 5/8, which is 0.625. And I'm going to add one more. So plus vars y vars function y1 and 0.875. 875. Now remember to close your parenthesis at the end. Close your parenthesis at the end so that you're multiplying the whole thing by 0.25. And then hit enter and you get your answer that way. So there's two ways to get your answer. And I did a similar calculation for the trapezoidal and the Simpson's rule, as you'll see, but that's how I chose to do mine. Okay, and this is your midpoint approximation from 0 to 1 with 4 subdivisions. Let's go back and I'll show you the trapezoidal rule and Simpson's rule. So here, let's see. So, okay, that was the midpoint rule. The only difference with the trapezoidal rule is the formula, okay? Now, the trapezoidal rule, you have delta x, okay? And your delta x is the same as the one we had before. It's 0.25, but you have a 1/2 out here. It's delta x over 2. And it has to do with the formula for a trapezoid, okay? So this is delta x over 2. And what you do is you start from wherever the left side of the interval is, which is 0. So we have f of 0. And then the rest of them until you get to the end get 2. Now, let me see if I can explain to you why this is. Okay, a little bit anyway. So what's happening here is that we have, let me see. Here's my curve. So we have a curve and we have 4 subdivisions. Something like this. And we're making trapezoids. So when we do that, remember the trapezoid has two sides that are not parallel to each other, right? And so what happens is that this first, I'm making 3 trapezoids. So this is my 0, this is my 0.25. I'm sorry, my 0 and then my my 0.25, my 0.5, my 0.75, and then my 1 out here, right? So what happens is that this first trapezoid right here on the left doesn't have any shared parts to it. This is just this first edge. This is f of 0. When I get to this piece, the second part of the trapezoid, I have to count this twice because this line counts as part of this first trapezoid. It's the right base, if you will, of this trapezoid. It's the left base of the adjacent one. So it counts twice, hence the 2 here. Same thing happens over here at 0.75. The right base of the one next to it and the left of the adjacent one, hence another 2 here. When I get to the end, this end only counts as part of one trapezoid. So the trapezoidal rule has a single instance of the first value, double instances of everything in between it until you get to the last subdivision. And I did a similar thing here. Remember, you're dividing delta x by 2. So half of 0.25 is 0.125. F of 0 is 1, which we get from putting it into the function. F of 0.125, 2 times f of 0.5, 3 times f of 0.75. I'm sorry, 2 times f of 0.75 and f of 1. Okay. If you add that all up and you do the arithmetic, you get the answer down below. Okay. Now, Simpson's rule is a little bit more complex as far as the arithmetic, but the process is similar. What happens with Simpson's rule is that instead of approximating our areas with rectangles, which is something that we're used to, or even with the trapezoid, what we're doing here is we're approximating this with parabolas, okay? So we're actually creating parabolas to approximate it. So we have something like this. So it's like you have a bump, you have a bump, and you have another bump here, okay? It's not a very good drawing, but there are better drawings in your book, and this is derived for you in your textbook. But again, delta x is b minus a over n, which we've seen. It turns out that Simpson's rule, or the rule of thirds, has a 3 underneath it. It's 1/3 of delta x. Okay. And we start just like with the trapezoidal rule. We start from the left endpoint, and this alternates 4 and 2 until you get to the last subdivision. Okay. So, but here you your delta x is 0.25. So this took a little while to get there. F of 0, 0.2, so 4 times f of 0.25, 2 times f of 0.5, 4 times f of 0.75, and 1 times f of 1. Don't forget about the alternate 4 and 2 structure, okay? Again, not derived for you in your book, but my answer was 1.11136 3. Okay. If I had made more subdivisions, or if I had made them unequal, then I would have had maybe a different approximation, maybe a better one. But notice how close they are. This is 1.10, this is 1.116, this is 1.111. Okay, so to 2 decimal places, they all pretty much match. This Simpson's rule would be a 100th off. Simpson's would be 1.11. The trapezoidal would give me 1.12. And the midpoint rule would give me 1.11. So you can be confident that that area is between 1.11 and 1.12. Okay. I hope this helps. This was just the computational aspect of the 3 rules that we're going to be looking at in this section. But I hope that this example helped you, and I will talk to you soon in my next video. Take care, everyone. Bye for now.